All right, we are doing transformers today. So we have, and the math is pretty basic. So understand that with transformers, there's two things. One, we got to remember that the coils. So if we have a coil ratio, so let's say we have primary coil over secondary. So primary over secondary will always have the same voltages. So coil 1 over coil 2 is going to be equal to voltage 1 over voltage 2. All right, so that's the first thing to understand. The second thing to understand is that we still have to always have power. P is always equal to IV. Power is always equal to current times voltage. So that will always be there too. Okay, so here we go. What will the voltage output be of the secondary? So we have 1,000 turn, we have a 100 turn primary, 1,000 turn secondary. So we have a coil ratio of 1 over 10. Okay, from primary to secondary. And we see that the primary has 120 volts AC. And again, it has to be AC. It cannot be DC. DC will never work with a transformer. All right, so we have 120 volts. So the voltage of the secondary is going to be what? Right, and so we just have to do our cross multiplication here. All right, and we get that the secondary voltage has to be 120 times 10 or 1200 volts. Okay, so we know that is 1200 volts right there. All right, now what's the current flowing in the secondary circuit? So we look at the secondary circuit and we see that we have 1000 ohms. All right, so we're going to do Ohm's law. V equals IR. Okay, in the secondary, we just figured out the voltage is 1200, and we were given the secondary of 1,000 ohms. So we have resistance and we have the voltage. So we do a little math. Divide both sides by R. Yoink yoink. V over R is going to be equal to our current. So we have 1200 volts divided by 1000 ohms, and that gives us a current of, so our I is going to be equal to 1.2 amps. So we have that as 1.2 amps. All right. Now that you know the voltage of the second current, or voltage in the current, what is the power of the secondary coil? So we know current is I. We know voltage V is 1200. So all we have to do is multiply those two together because P equals IV. Okay, so power equals current times voltage. We're going to have 1.2 times our 1200. Okay, so 1.2 times 1200. And we get 1440. So we have 1440 watts is going to be the current or the power for the secondary. Okay, now here's the key. And it says neglecting heat loss. Okay, we're not worrying about any loss of energy from anything. We're doing ideal stuff. So since we know that conservation of energy means the total energy has to be the same before and after, that means that the current or the power here before had to have been 1440 also. Okay, so that's the key for all the stuff with transformers. We need to remember that the power will always stay the same. Okay, so we go to, we know the power, we know the voltage. Let's figure out what the current is going to be. So we have our power, which we just figured out was 12. So we're doing P equals IV again. We know power, we know voltage. So let's divide V on both sides. And we see that I is equal to P divided by V. So power is going to be equal, or power was 1440. All right. And our voltage for the primary was 120. Okay. So we have our 1440 divided by our 120, and we get a current of 12 amps. Okay. So what you need to understand, this is a key for current and transformers. Transformers will step voltages up, and when they step voltages up, the current has to go down. The power has to stay the same always. Okay, so you could either have a very high voltage and a very small current, which is helpful, okay, or you can have vice versa. You could have a very high current or very small voltage, okay. The whole reason that we send voltage across the country in really, really high amounts is that the current stays down. So we have low current, which means we don't lose as much energy as the electricity goes across the country, which means we have to have the voltage really high. Okay, but then we can go to a transformer, and when we get to a transformer, especially the one right outside your house, then that voltage that could have been 68,000 volts somewhere or 13,000 volts a little closer to your house drops down to 120, so that you can have a little bit more current, and you can have current running through your house. Okay, all right, so here we go. Let's circle answers down below too. The results show that voltage is stepped up from primary to secondary. Is that true? It went from 120 to 1200, so it stepped up. Okay, and that the current, that means, would have to step down. Okay, for a step-up transformer, there will be more turns, more coils in the secondary. There has to be more coils in the secondary than in the primary. For such a transformer, there is going to be less current for the secondary. Okay, a transformer can step up voltage or step up energy and power, but in no way can it. So it can only step up voltage. Okay, we cannot step up energy and power. There's no way that you can create more energy and power. The energy and power still has to stay conserved. Okay, so that's the right answer for that one. If 120 volts is used to power a toy electric train that operates on 6 volts, then a step down would be needed, right? Because you're going to go from 120 to 6. That means you're going to have to step it down. Okay, and then the ratio would just be 120 divided by 6. So 120 divided by 6, all right, and that's going to be a 20 to 1, all right, to drop down. A transformer operates on only AC. You can never do this on DC, which is why Thomas Edison had so much trouble because he really held the whole electric company back, General Electric, because he did not understand AC. And so that means power could not travel as far a distance across the country like AC could do. Okay? And again, because it's AC, because the magnetic field constantly changes. When you have the current going back and forth, back and forth, back and forth, it continuously changes the magnetic field, which causes the current from this side going back and forth, to cause a current on this side. Okay, that is it.